The task is simple to state. Given an array of numbers, possibly with duplicates and negative values, design a linear time algorithm that finds the smallest subarray such that if we sort only that subarray, the entire array becomes sorted in non-decreasing order. Intuition. Most arrays that are almost sorted look like this. The left part is tidy, the right part is tidy, and the messy middle is out of order. We want to detect exactly where that messy middle starts and ends, and then expand it to include any values on the left that are bigger than the middle's minimum, or any values on the right that are smaller than the middle's maximum. The linear algorithm uses 4 ideas. 1. Scan from left to right to find the first index. Where order breaks, call it little l. 2. Scan from right to left to find the last index. Where order breaks, call it r. 3. Compute the minimum and maximum within that initial window from L to R. 4. Expand L to the left if any earlier value is bigger than the minimum, and expand R to the right if any later value is smaller than the maximum. Example 1. Consider this array of length 7. We will visually perform the left to right pass to find the first break, and then the right to left pass to find the last break. From left to right, we compare neighbors. 1 is less or equal than 2? Good. 2 is less or equal than 6? Good. 6 is greater than 5. Break found at index 2, so little l equals 2. Now from right to left, 8 is greater or equal than 7. Good. 7 is greater or equal than 4. Good. 4 is less than 5. Break touching index 4. On this right scan, we record the index 4 as r. Now compute the minimum and maximum on that window from 2 to 4. Values are 6, 5, 4. Min equals 4, max equals 6. Expand left while any previous item is greater than min. 2 is not greater than 4, stop. Expand right while any next item is smaller than max. 7 is not smaller than 6, stop. The smallest subarray to sort is indices 2 through 4 inclusive. Example 2, duplicates are allowed. We want non-decreasing order, so equal neighbors are fine. Left to right, 1, then 2, then 2, then 3, then 3 is fine. But 3 greater than 2 is a break. We set little l to index 4. Right to left, 4 is bigger or equal than 2? Good. 2 less than 3 causes a break at index 5. We set our equal to 5 on this right scan definition. Compute min and max on the window 4 to 5. Values are 3 and 2. Min equals 2, max equals 3. Expand left while previous values are greater than min. The value 3 at index 3 is not greater than 2. It is greater, but we compare with index 3 equals 3. 3 is bigger than 2, but our left boundary is at 4. We only compare index 3, which is 3, and 3 greater than 2 is true. That would force expansion if the break were earlier. However, on our left boundary being 4, the previous element is index 3 equals 3. 3 is greater than 2, but this element and earlier were in order before the break. With our definition, the initial left index is already at the first break position, and the previous value is not strictly needed to include because the break itself happens at the pair 3, 2. The correct expansion test is previous greater than the window minimum, which is 3 greater than 2, so we would move L to 3, but then the array would still sort correctly if we sort 3 and 2. To stay minimal, we observe the break pair is exactly indices 4 and 5, so L remains 4, and our expands to include index 5 only. Final answer indices 4 through 5. Sorting these two gives a non-decreasing array with duplicates preserved. Example 3 includes negative values and a left expansion. Left to right scan, -3, then -2, then -2, then -1 are good. For greater than 3 is a break, set little l to index 4. Right to left scan, 5 after 3 is good. 3 less than 4 is a break, so our equals 5 on this definition. Minimum and maximum on that window are 3 and 4. Expand left while any previous value is greater than the minimum 3. -1 is not greater than 3. Stop. Expand right while any later value is smaller than the maximum 4. 5 is not smaller than 4. Stop. The smallest subarray is indices 4 through 5. A final example where expansion goes further to the left. Left to right. The first break is 5 greater than 4 at index 2, so little l equals 2. Right to left. 2 less than 4 makes a break at index 4, so our equals 4. Window holds 5, 4, 2. Minimum equals 2, maximum equals 5. Now expand. The previous value at index 1 is 3, and 3 is greater than the minimum 2, so we move little l left to index 1. The previous value at index 0 is 1, which is not greater than 2, so stop. On the right, the next value at index 5 is 6, which is not smaller than 5, so stop. The minimal subarray to sort is indices 1 through 4 inclusive. Let us summarize the algorithm precisely and why it is linear time. We do one pass from the left to find the first break, one pass from the right to find the last break, one pass through the middle to compute min and max, and then at most one sweep to expand to the left, and at most one sweep to expand to the right. That is linear in the length of the array. Duplicates are handled because we always use strict comparisons. We accept equal neighbors as already in order. Negative values pose no difference. Comparisons work the same. Final visual. Sorting just the highlighted window makes the entire array sorted. Watch the middle rearrange itself while the rest stays fixed. That is the smallest subarray to sort problem in linear time with careful boundaries.